Actually, I was able to grade them pretty fast.
Thank you.
Because,
That was awesome.
again, well, it worked out. I guess you were one of the happy people, maybe, okay?
It was nice having you.
So, yeah, it worked out because the multiple choice that you had to answer there were pretty easy to grade, and obviously most people, almost everybody, got full credit on the cardiovascular thing. I can literally kind of scan that. Everybody did it right away, so that helped. So overall, again, well, it sort of depends on your perspective on things, as far as. Wait, is this the right one? As far as the distribution of the test. Now, generally, what I observed, and I'll put up sort of the distribution of grades. Generally, what I observed is sort of a crunching, where people that hadn't been doing well on some of the first two tests actually moved 10, 15, 20 points up. I've had a couple people, which is really cool. I mean, again, some people are really upset, and so I'm not talking to you at the moment. But I am going to mention this. But I actually had a couple people who got C's on the first test, got B's on the second test, and got A's on this. And as everybody, most people can realize, this was the hardest test. So doing whatever you guys are doing, I mean, that's what you're doing successfully. I've had a couple A's move down, and that isn't that cool, and you're not happy about that, but there's two tests left. So the overall distribution is sort of like this. And I'll tell you a little about, I don't want to say it's a disturbing thing, but just so you can kind of note from other classes. So there were, with the curve, and the curve's already figured in, 10, 17, and 12, and just sort of 4 and 2 of that. So sort of an A, B, C type range. And it's actually really good. I mean, if you look at those percentages of A's, B's, and C's, it's fine. Usually, though, this is 22% A's or something. Yeah, my other classes, other schools have about 28, 29% A's. So that's why some A's seem to drop down to B a little bit on this compared to others. That was just sort of the result of this test. So it's a difficult test, and again, you can have your opinions on the questions, but they're my questions. And so these are going to be the last two tests you're going to have. Will be very similar to that. So again, it's hard to switch teachers in midstream here. So if you want to do better, talk to me more. We'll look over those questions. You'll see sort of the reasoning of the questions. And again, I'm there before class usually, not today. And I stay, labs end out early. I'll stay as long as people need to go over this material more specifically, and hopefully you can do better on the test if you didn't do well. If you did well and you're in the right range, definitely keep it up. But we have 2 exams left. That will be, I don't want to say as difficult. Most people think the cardio was the hardest one. The material coming on the next one, I think, is the most comprehensive. But usually people do better on it. I think it becomes clearer because you guys are getting smarter as well. So there's those points. I've got to figure out, right, and I'm going to let you know by next week. On the labs, on the schedule we have like a lab quiz, and it's really messed up because I don't want people. There's no way really to do a full lab quiz before the Thanksgiving week. I don't want us to do it after the Thanksgiving week, because then you're like studying Thanksgiving week, which is not going to happen. Okay, so not in my class at least. There's no way I want people studying this. I want you actually with having a break. So I'm going to figure something out. Maybe a couple mini quizzes within the lab or something that, and I'll let you know ahead of time. So it's really not going to be something that you're going to have to worry as much about. And really, it's going to be, we'll have some blood typing problems before this one lab or something like that, or something like that. Or some sort of take-home assignment, something like that. Something where it's going to give you an opportunity to move up your grade overall. But the real opportunity are these 2 exams. So we have 2 more exams left. There is that, again, sometimes I mention after this, there is that optional cumulative, which is actually the very last day of class. We have this thing carrying over to the following Monday. That happens sometimes. So I'm going to be giving the test number 5, which is on the material, on the Wednesday, okay? And so that's for a lot of people. First of all, you'll have that grade right away, because it'll be all multiple choice. Run them through, put it in. You'll see exactly, if you do nothing else, what grade you'll have. If you are, especially for people, again, people that got C's or D's and now you're getting B's and A's, it might be that you only need, to move that up 7 points to get your grade. You'll be that close, or 10 points. And that's real doable. Okay? But if you're like an 88 and you want a 95 on the cumulative, that's hard. Okay, that's just harder to do. But you'll know. And so if you think it's going to be worth taking, the cumulative can't hurt your grade, but you'll know at that point, that Wednesday, whether it's worth trying or not. And if all you need is 10 points or so more than your previous one, hey, it might be worth it. Otherwise, it probably isn't.
So the cumulative will replace any test score?
Yeah.
Okay.
Well, yeah.
Your lowest test?
Well, we'll replace, no, actually, I'll have to qualify it. We'll replace test 1 through 4. So that 5th test, which is our last day, it can't replace that. So you sort of have to do that. But it will replace 1 through 4. Again, if you do worse than any of those, it just goes away. So it can't hurt your grade. But luckily, the way we're doing it this way, you literally don't have, you'll know whether it's even worth taking or not. I mean, you'll have your grade Wednesday, and again, if you need a 98 on it, well, that's up to you. But overall, the idea is usually it's when you've done poorly on one test and you've done well on the others, and you just have to bump that lower test up by 10 points or something like that. And plenty, about half the people it's done and half the people it's not. I mean, Lynn, how many people have been using Lynn? Is Lynn still around? Okay, I haven't seen much. She's probably the only person, maybe one of the person who got an A on that. Because if you talk to Lynn, you just see her motivation, and so she's sort of a determined person. And all I can say, and I'm going to say one more time overall, a lot of success here is even if you've done poorly, not to sort of just give up or just, you can complain to each other about the test, but when it comes down to it, they're still my test. And so, just figure out a way to conquer them. Obviously, some people are conquering them. Everyone in here can. I know everyone in here is learning. There's no doubt about that. I have no doubt. It's just whether, tests are a small part, let's say, of all life and as far as what you're doing, but it's sort of my part, okay? My part is to sort of separate people in divisions based upon their ability to translate this material into tests. These tests, if you go ahead and buy those books on, practice MCATs and T's and all those other entrance exams, you'll see multiple choice questions, very difficult questions. If you can master my tests, I mean, I've had people come back, it helps you on those tests as well. And that's my rationale. My rationale is not to torture people or anything at all. I like when I run those scantrons through and I just hear beep beep, okay, or small numbers. And sometimes I do. The high grade I think was 104 with the curve. The curve was 9 points plus one question which was a bad question. I had one thing turned around, so in a way 11 points. But somebody only missed 2 multiple choice questions. There was another one missed maybe 3 or 4. And so, but the idea really is the tester there, go ahead and look to see what you missed, how you missed the question. Again, interpreting my questions and looking at it, there's really only one right answer. It's just sort of how can you find it. So look at that. And take more time on it, and then you can actually see. But again, don't think that if you only got an A or a B because of the curve, don't think you really got a lower grade. You didn't. That's how these tests are meant to be. The tests are meant to be to, again, distinguish these groups of performance here. So if you got an A on this test, I don't care if you got 104 or you got a 91 after it, you've earned an A on the test. And same thing with the B. And again, overall, pretty good distribution, if you look at the distribution. But a few people are unhappy, and but we can counter that, start sort of moving on here. Any questions before I sort of begin what we're going to do?
Just a quick question. So when you say 2 exams left, you mean 4 and 5, and then not including the optional, right?
Exactly.
Okay.
So 2 real exams that will count for your grade, 200 more points of that. And again, somehow we're going to take in those lab points. Probably the pulmonary lab, which we're doing now, will be another one of those turn-in labs that you'll get points for that. And so I'll start making up, some of those points of just, accomplishing the lab.
For final grade, what percentage do you have for
90. So, basically, it's sort of 90, 80, 68 as far as A, B, and C. So C, it goes down a bit because, either you have to just pass this class or you're in the group sort of that needs A's or B's, for nursing. And so those ones are pretty strict. Again, I do round up, but I don't round up from 87 to 90. But I'm not one of those people where, and generally too, if I kind of see 89.1 or 2 and you've gotten good grade on the last couple, you can almost figure I'm going to round up. But some people are 89.9, you've got to be because all that. I can't deal with that too much. You're dealing with a couple points, going from a grade, and you know, I don't really do that. But, you know, there's a limit how far can you go. So usually, you know, if you've done well and you kind of get to that 9 mark here, or that 7 mark here, you can pretty well be assured you're going to get that grade. Okay, so I do round up. But officially, 90, 80,
And it's just
60.
straight A's, no plus minus.
There's no, I hate plus minus. I mean, I can't deal with it at any school. So this is bad enough, okay, just to have grades like this. Any other questions? So, what we have in this next section is the following. And this will be sort of the best section. This is where we're going to sort of culminate the course, because we are going to do, after we do respiratory, we're going to do the kidney and really the whole renal system, which is going to tie in all the systems that we've done. I promise you. It's going to be, you're going to be able to do an amazing thing after a couple weeks. And again, we have the schedule where the test will be, and I'm pretty sure, right? Otherwise, no, I'm sure. I've scheduled it so it's before Thanksgiving break, probably that Wednesday right before. So the key is, whatever's going on the rest of your life, forget it. Okay? I mean, seriously, forget it. You know, tell your husband, wife, girlfriend, boyfriend, like, I'll see you in I'll see you at Thanksgiving. Okay? Right around then. Because again, everyone, if you could just devote your life to me right now for the next couple of weeks, you're going to ace this test. You're going to learn stuff you're never going to forget, and you're going to feel a lot better going into the break. Because I want people to feel good going into the break, and then you literally will have a break. I mean, you won't have to think about. You'll be through the hardest part of the course. The last section, even though the tests are so hard, I ease off on material. And you know, and you literally can take a break and not think at all about physio. But you've got to think about physio 24/7 for the next 2 weeks or so, okay? And you know, I'm trying to make pictures to make us feel good, okay? All the respiratory ones, you know, I'm like, breathe in, let's think good thoughts. And a lot of it is a good attitude here. So try, if you did badly, try to forget it, okay? I want us to all do good. It's going to be cool stuff, I promise you. Maybe not this chapter, okay? But what we're going to cover is this. 4 chapters. 17 and 18 are the respiratory system. And of those two, 18 is the more difficult one. That's going to involve gas exchange, but I've got a way, with Stu sort of helped me out to begin with, we've got a way to explain that sort of makes it a lot more sense than if you just read the book on that. 17 we'll get through today. The lab actually will kind of get to it too. We have some math things. If you like math, how many people like math? A few people. So you're going to like this chapter. We're going to have, and part of the questions, we're going to have some gas laws we're going to deal with, okay? Then 18 we'll do that. Then, and I need a drink, you know what's coming. No, it's not an oh-oh. It's an oh my God, I can't believe what I know. I promise you. This is a money-back guarantee. Okay? Money-back guarantee. By the end of chapter 20, which again, it's not just chapter 20, but it's what we add to it, you will know so much that it's crazy. And I promise you will. I don't care what you do on the test. Well, you care, obviously. But there's no way every person here is going to be able to relate basically how blood pressure, if the kidney's going to respond to that, how all of a sudden that's going to cause a problem with the potassium levels, how the kidney will respond to that, but then we'll have acidosis, and then the respiratory will respond to that. So that when you're looking online, and you're actually looking at, let's say, a patient, a lot of people are in healthcare, and you're looking at all these symptoms, or drug, contraindications again, you're going to see for an ACE inhibitor, which is going to be for blood pressure, look out for metabolic acidosis and hypokalemia. And again, that's memorizing things that are just sort of a list, like, tachycardia was. You won't be a list anymore. You'll literally see how your systems are trying to respond and some of the side effects that can happen, and you'll know why you're looking for hypokalemia, why you're monitoring potassium levels. Everyone in here will be able to do that. And the cool thing is, we'll be able to start with anything. If it's a pH problem, we'll see why it's going to affect blood pressure and respiratory system and pH levels. If we start with a pH problem, we'll see why we can do the other 3. A blood pressure problem, what happens? So you literally can play the game sort of with 4 balls in the air. And that's a money-back guarantee. Money-back guarantee, okay? Please don't. And now it's being recorded. It's going to be on the internet. I'm in trouble now. He said money-back guarantee. So 19 and 20 are the kidney. Again, 19 is going to be sort of the intro to it, sort of the easy chapter. And then 20, the big boy. Okay? And we're going to spend several days, going on chapter 20 and those extra questions of how to play this game. Okay? And so we'll have plenty of time to do that. Again, a couple weeks, what is it to Thanksgiving? Maybe 2.5 weeks or something like that? Or 3. That's what we've got to do. If we can do this together, boom, we're all going to be happy. I hope. All right. So this chapter isn't the best one, but I'll show you kind of what we need to know from it. We're going to learn how to breathe, basically. And we'll get through a lot of it today. This was the original picture I had. I thought it was cute, but then I found I'm having trouble with this today. This thing's not working. I found this one. I thought it was just nicer. So, especially, you know, in San Diego. Got it. This thing is like causing all kinds of weird things. All right. So if we look at this first slide, I'm not going to ask, you know, list the 8 steps of how to breathe. But when you look at this, and you can kind of see this, we have a commonality, a common word here. Diffusion. So all gas exchange is going to be by diffusion. And diffusion is going from what? High concentration to low concentration. So why oxygen is going to go from the lungs into the blood? Higher concentration of oxygen here than in the blood. Why is it going to go in the tissues? Same idea. In the arterial blood, we have a higher concentration of oxygen than in the tissues. It's going to diffuse from high to low. Same thing about CO2. Basically, those gases are going to go from high to low until we get rid of it. So it's all about diffusion. But we're going to exploit that as we go. So a major process we talked about in the first one. Now, if I'm not going to do anatomy, right? I don't do anatomy. So it's on my contract. So we're not labeling all this. But we are going to just sort of mention a couple things. You know, there's the upper respiratory tract, and there's sort of the list of it. And then there's the lower respiratory tract. And, you know, we're going to mention just a couple functions, because this is a function class of the upper respiratory tract. It'll be like 2 slides. But we're going to be concentrating here. And specifically, we're going to be talking about the bronchioles and the alveolar cells, because this is the site of exchange. And this is going to be the control of it. So really what we're going to be concentrating on are the last segments here. Okay, just putting a picture up, what we can see as we descend the respiratory tract, we're branching more. By the time we get to the alveoli, we have, you know, hundreds of millions of them. What are the advantage? Why are we branching and creating all this? Surface area. Structure, function. The function, and we'll basically do it in the next 2 slides too, if the function of the system is gas exchange, we want the maximum amount of surface area between the gas and the blood. That sort of makes sense, right? So we're going to literally have, there's a table later that talks about how many of these, we're going to have this, you know, increased in numbers and numbers until we get to the alveoli. And the alveoli themselves are going to be spheres, which some mathematician says is the one that has the highest surface area as far as the shape. And I'm like, okay. So we're creating the greatest surface area. And what are they surrounded by? Blood vessels. Seems to make sense, right? Structure, function is for gas exchange. We have millions of these alveoli surrounded by blood. Lots of blood vessels. Okay? Here's the other thing. Okay, besides being highly vascularized. In fact, let me actually, do this slide. I mean, you have it on your handout. But the other idea of, you know, matching structure function is for this type of tissue. You know, we don't want multicellular layers with a lot of extracellular matrix. We want exchange epithelium, as we learned in the first section. And that way we're going to have basically just 2 cell layers. Okay, here's the cell layer of from the alveoli. Here is the blood cells, and a very thin basement membrane between with very little fluid under normal conditions. This will be the maximal ways we can do the gas exchange. So sort of 2 structural function ideas, being highly vascularized and having all those capillaries and bed right around it, and kind of, again, what I just said, but what's listed on here as well. Now, surfactant. If you go back to, if I go back to the previous slide, I can't, I don't know what's wrong with this thing. If you go back to the slide, you know, I actually defined 2 types of alveolar cells, type 1 and type 2. And type 1 are what I've been talking about. That's going to be the ones for gas exchange. Type 2, and you can see them interspersed here, basically secrete something called surfactant. And right now we say it aids in breathing, but I want to sort of tell you how. How many people have heard of surfactant? Okay, here's going to be the key. We're going to show you I'm going to talk about the function of it. And you can see what it's doing right now from this picture, and, by the figure. It's lining the in-surface, the inner side of the alveoli. And so if I start to make my beautiful pictures, okay, here's our alveoli. Here's going to be our bronchioles, by the way, which are going to control airflow. But here's the key. Let's talk about expiration when we're breathing out. Okay, so this is going to be expiration. And so as we're doing this, we're going to have all of our alveoli start to collapse, okay, because we're squeezing the air out. Now, sort of on the inner surface, like most of the cells we have, there's water, okay? There's basically a layer of water. Water is within our cells. And as you get closer and closer, water tends to basically come together, right? If we pour some, I don't know about the vitamin water work, but if we pour some water out here, it stays together sort of as a drop because it has surface area. Surface tension because of the hydrogen bonds, right? So it stays together. So what will happen if we don't have something to help us here is when we expire, you can have these balloons here, all the alveoli completely collapse. Then the next time we have to put air in, we've got to go from a completely collapsed balloon and fill it up. Do you think we want to spend that much energy? Do we want our alveoli to completely collapse when we breathe out?
No.
Surfactant. Surfactant's like a soap. Okay, if you take a drop of water that has the surface area and comes together, and you put something that's soapy, something that's hydrophobic, it's going to break up, decrease the surface tension. That's what surfactant does. So I don't have my other colors there, but I'll put it here. You can see it lining it. So the idea of surfactant is that it's going to decrease the surface tension of the water, sort of the water that's sort of surrounding this. And what the basic idea is going to do, it's going to prevent, here's sort of the big bullet points, because I'm not really into the physics of it as much as just to mention it, but here are the two big things. For surfactant, it's going to prevent alveolar collapse, total collapse, during breathing out, during expiration. So that less energy is needed for inspiration. So by preventing total collapse, the next time we have to fill up all of our alveoli, there won't be as much energy. If we totally collapse the balloon and have to blow it up from scratch, it's going to require a lot more energy to actually breathe in. And that's why, for premature babies, they're sort of looking for, they don't want to, if possible, deliver before the baby has sort of developed that surfactant, or else breathing will be, much more laborious, otherwise. Although I think they can give you surfactant now and all that. I was a premature baby because I couldn't wait to get out here and talk about the kidney. And that was a long time ago. I think they've improved methods, but my lungs are really strong. That's why I can do all that biking. So that's like the one thing I have. I mean, I'm a short little guy and I can't really do much, but my lungs have helped me. I can't go fast, but I can just keep on going. Right? It's like 200 miles, 300 miles. Part of it is my strong lungs kept me here. But anyway, that's surfactant. Does everyone sort of understand the two bullet points I sort of want with that? So those are type 2 alveolar cells. They're basically throwing out their surfactant, which is going to help prevent these from collapsing, so we don't have to take as much energy to inspire. Okay, those are the two bullet points. Similarly, in a way, what I'm going to put right over here, because it's a very similar concept, is our lungs are surrounded by these pleural membranes, a pleural sac. Okay, you can kind of see it here, sort of the analogy of what it's like. It's fluid-filled, and it's like if you took a fluid-filled balloon and sort of wrapped it around your lungs, okay, the area of your lungs. and it's fluid. It contains fluid. Now the key with this is, as it says too, it's much thinner than it shows here, is I'll kind of show you this picture, and then we'll put the two functions of it. It's going to work in a similar way that the intrapleural pressure, so the pressure of the fluid in the pleural membranes is negative. So it has sort of a sucking force to it. And so what you want to think from this picture is the same idea. When we're expiring, okay, when we are blowing out, do we want our lungs to completely collapse? No, because, and there is this idea, our lungs are elastic, hopefully, or else we have a problem. That means that when you start expiring, they sort of want to collapse. We need an opposing force. By having this negative pressure, and you can kind of see the arrows here, it's basically preventing lung collapse. Okay, I'm going to put that up there. That's why it's a very similar idea. That's why I like to show it next, right? Here's the idea to prevent, individual alveolar cell collapse, but we have this idea for the whole lung space as well. So they'll be surrounded. The other thing it does here, I'll put, is, we got ribs out there and stuff, and it sort of cushions so you're not sort of, hitting the ribs. So a very similar function, because we're about the function. So we have the pleural membranes, which basically same idea. Because it's under negative pressure, kind of go the same bullet point. It prevents lung collapse during expiration. And again, just like this, that's good for us because we don't want to go from scratch again. It takes too much energy to breathe in with a totally collapsed lung. It really would be very difficult at that point. So that's what the pleural membranes are. Negative pressure to do that. And of course, the other bullet point I have to put over here is the fact that it sort of protects us from the ribs. Okay. Now, what if one of my students, not here, but maybe another school, comes, I'm in the parking lot and stab. What do we call that? Justice. No. We call it a pneumothorax. Okay, so here's the idea. There's a knife that almost got me, but I have somebody who got a name who's going to help me, right? But the bottom line is this is where you can have a collapsed lung. Now you have this idea. You've broken that seal, and now we have atmospheric pressure sort of equalizing on both sides. There's no way you're going to get air in that lung unless you sort of correct that. So this is why we sort of need that space, the thoracic cavity and this interpleural negative to keep us being able to expand the lungs. Because what we're going to do now, talking about breathing, it's all about pressure differences. What's the atmospheric pressure versus what's the lung pressure? And if we have this equal, where the pressure surrounding the lungs is equal to what's coming in, you can't actually expand. We need a difference in pressures.
When someone has a collapsed lung, is it the pleural sac that it...
Well, you basically have you've punctured, and it's actually gone through and basically punctured the whole thing. So you definitely punctured the pleural sac, would have that negative pressure. But then the bottom line is the whole thoracic cavity, which is air-filled, now is the equal pressure to what's coming in, and there's no way you can do this because we need the pressures to be different. But we have actually punctured it.
Thorax is the process of
Yeah, that's what's created, right? By sort of puncturing that seal. All this is showing you, people that like to see math, you're not memorizing any of this stuff, what we said before. You can actually see, it says how many trachea, bronchi, smaller. Okay, here's what we're going to concentrate on. But the bottom line is, if you look at this, we can see we have, 3 to 6 times 10 to the 8th alveoli. And so if you look at the cross-sectional area, surface area, we've increased it 1,000,000-fold by doing this descending and making more and more and more. So it's just a number that matches. You don't have to, it's not going to be on the test. But just so you kind of see, that is the idea. We're going to basically maximize the surface exchange, which is what it's designed to do. All of our systems, the more you learn about them, the more you see the beauty of structure-function relationship. And if you do anatomy, you know the names of everything. But now with this class, Again, if you haven't had anatomy, you'll learn the names of it then. But here you really see how things go together to work, and it's really, I know, it's really amazing. Okay, I said we were going to say just a couple things about the upper respiratory tract, and here they are. So, functions of the respiratory tract. Before the air reaches those alveoli, which are very thin, very sensitive, as we go down, we want to do the following. We want to warm the air. We want to get it to our body temperature. We want to get some moisture in it, okay, humidified. We don't want 100% dry air trying to reach it. And we want to filter it. And the first part of the course, again, we're sort of using those names of the 5 types of epithelium we talked about at the very beginning. We just did exchange. Here's ciliated. And there were 2 places we had ciliated epithelium, and that was the upper respiratory tract and the female reproductive tract. And the key with this is cilia have movement. And so in this case, that's part of number 3. That as long we're inhaling things from the external environment, air, but we also have particulate matter and bacteria, etc. We don't want that reaching the bottom. So we have this upper respiratory tract with sort of mucus and cilia, which will trap the particles, and then the cilia will help move it up the respiratory tract so we can cough it out or get rid of it. So that's what the upper, as far as we're concerned, what we need to know about the upper respiratory tract. Warms it, humidifies it, filters it. It's not the most exciting chapter, but we're going to get through it. I'll try to jump around a little bit. There's one cool thing we'll get to before we're done with the chapter. This is just nuts and bolts, and I have all that. So, how do we breathe, right? Let's show you. It's going to be very similar to how blood flows. We're talking airflow, and we're going to be talking, it's going to be a difference in pressures, and resistance. And we talked about, when we did the cardiovascular, if these were vessels, okay, blood vessels, we said that. We said flow of blood was going to be determined by the difference in pressures, that's sort of how we're indicating different between one side and the other, and the resistance. And a lot of that resistance was controlled by these arterioles, which constricted and dilated. Same thing with ventilation. Now, with ventilation, if we sort of take our alveoli, or even, let's get to the whole lungs here, because I love my lung pictures. Okay. And I'm never good at lungs, and they always look bad, so you gotta just deal with it. Okay? So, I'm sorry, my art classes just don't work, okay? And actually, I should make it, well, we'll be fine on this overall, okay? So, these are the lungs. Now, the key with this is the thoracic cavity, because we're going to use this to breathe in a minute. Okay? This is the airfill cavity around the lungs, which is going to have a pressure. This represents the lungs, or we'll say the alveoli. And this, which maybe I can make it a little thinner here, are the bronchioles. And they're going to constrict and dilate similarly to the way these arterioles constrict and dilating. They're going to help control resistance to airflow in and out of the lungs. So we're going to be talking about that. But everything else is going to be the same, the idea of pressures. And really, we have, I wish I had a different color, but we have atmospheric pressure. And overall, we could talk about, alveolar pressure within the lungs. We'll also talk about the thoracic pressure surrounding it, in a minute at least. But let's just look at these top 2 pressures, atmospheric and alveolar pressure. Okay? In order to breathe in, which one has to be higher? Do we need higher atmospheric pressure to breathe in, or do we need higher lung or alveolar pressure?
Higher
Atmospheric, right? We need, things are always going to go high to low. And so we need atmospheric pressure. If we can make atmospheric pressure greater than the lung pressure, we're going to breathe in. If we want to breathe out, we need to do the opposite. We need to have alveolar pressure greater than atmospheric, and then that's going to allow air to flow that way. So that's what we're going to control with the diaphragm mailing by breathing, okay? We're going to control these pressures. We want to breathe out, and again, this will be on this. We're going to basically create pressure here to breathe out. If we want to breathe in, we're going to decrease this pressure, and that will happen. And I'm going to list this in steps. But I sort of want to get kind of the overall picture before we do that. And part of that, I mean, it's on the slide too, right? If you have my handout or a slide. Okay? Atmospheric versus alveolar. Inspiration occurs when alveolar pressure goes below atmospheric, and we're going to show you how. So, again, this will go in if atmospheric pressure is greater. But we're going to control this by breathing by the diaphragm. Okay, this is not on your handout, but we're gonna do problems on this, and you're gonna have to know it, you know, for the test, for both tests actually, if I do a lab quiz. And not memorizing the gas laws, but we're gonna actually do some math with them. And one of these is gonna relate to when I come back to here of how we breathe. But if you just look at these laws right now, you're not gonna have to know what is Dalton's law or Boyle's law. We're gonna play with them in the next few slides. You can kind of see the second one is simply kind of what we've been saying. Gases are going to go from high to low. Okay, that's the gas law. That's fine. Now, these two, we're going to show you some math of it. And so the first one, and this is again, if you printed out the lab or if you got my message, you know, you'll see extra problems at the end. And I think even I might have more sort of demonstrating these laws. So this one basically is the pressure of a mixture of gases is adding up the individual partial pressures of the gases. And the best way to look at that is actually look at a slide. So this is the idea of this, and this is what you're going to have to do. If you look at the atmospheric pressure, okay, so you're talking about the air we're breathing in, we might be a whole number here like 760. 760 millimeters of mercury. We might have differences on elevation, but that's sort of the key. It's a mixture of gases, though. And here are the main gases, and we can see oxygen is only about 20-21% out of what we're breathing in. And we like to know when we're following gaseous oxygen through our body, what is the partial pressure of oxygen? Okay, because of all this that we're breathing in, we're sort of carrying, we care about carbon dioxide as well, but we want to know how much of the air we're breathing in is actually containing oxygen. What is the partial pressure of it? So to demonstrate what this law basically is, or to be able to do it, is the following. Okay, given this. And right now we're going to talk about dry air, which means there's no water vapor contributing to that number. So if you want to figure out the partial pressure of oxygen, under these conditions, what are we going to do? How do we get that number? Well, the total pressure is what? 760, okay, of all those gases. So if we want to know how much of that is oxygen, and we're given that numbers, what do we do to it? We're going to multiply by 0.21, right? 21%. Because 21% of that is oxygen. We want to know, well, what does that add up? What does that add to pressure? If you take 0.21 times 760, you'll get 160 millimeters of mercury, which is like, so the main air we're breathing in, because that's actually kind of, atmospheric pressure in general, will be containing about 160 partial pressure of oxygen of about 160 millimeters of mercury. So be careful, because we're going to follow the concentrations of oxygen as we go down. So, but that's sort of demonstrating, and what you're going to have to do on test questions are sort of like if I give you a number here and give you a percentage, and I want to know the partial pressure of oxygen, you simply are going to take, or any of these, you take whatever these percentages are, multiply that by what the total is, and you'll get the partial pressures. How about if we have, you're not going to memorize, what these are in that sense, but this has to do with humidity, this has to do with water vapor. And so if you're looking at atmospheric pressure that has water vapor in it, that means it's contributing to that number. But we still want to know these numbers. So what are we going to do? We're going to take, if we want to now, let's say we want to determine the partial pressure of oxygen under these conditions in which we have 24 millimeters of mercury contributing to that. Okay? How do we get that number? Well, I'm going to start at 760. What am I going to do to 760?
Do you still multiply by the percentage of that?
I will, but do I do that first?
Or do you want to subtract the 20?
I want to do that first. So you want to subtract the contribution of this by the water vapor and then multiply it by this. So we're going to subtract 24 because we don't care, that's not gas, but that's contributing to that pressure. We've got to get rid of the water vapor. And I'll give you whatever it is. You don't have to memorize under these conditions. But if it's 24, that's going to be what? 736. Then you multiply that by the percentage, 0.21. And when you do that, you're going to come out to 155. And that's, again, you're not going to have to memorize Dalton's law or anything like that. You're going to literally, whether I put it on this test or not, we'll see, but it'll be on one of these things. That's what we have in lab when we're practicing. You'll have, these will be blank. I'll give you this. I'll tell you if there's any water vapor, and I'll give you the percentages, and you have to just show that you know how to calculate that. Again, in dry air, which I'll say, is 0, you literally just take whatever that number is and multiply it by that, and you'll get it. If you have humidity, you subtract this from that, or whatever number I give you, and then you multiply by that. Boom. That's it. Any questions about that? Now, again, words can be, some people like this, but we're going to show this. This is more important for us breathing, and I'll show you a problem we have too. Boyle's law is basically saying there's an inverse relationship between pressure and volume. And the best way to actually look at that to get it is here. And this is going to relate to breathing in a minute. And it's a really nice figure because it's real simple. And so we have this idea that we have gas molecules sort of at a given amount and a given volume. And then what's creating pressure, again, are these molecules pounding against the walls of whatever cavity it's in. And so here we have the idea we have the volume of, let's say, 1 liter, and this much gas is creating a pressure of 100 millimeters of mercury. Okay, that's where we're starting from. Now, if we decrease the volume, well, just in general, if we decrease the volume, what do you think is going to happen to the pressure? Increase. And we can see this. See how this figure is really nice. I mean, now these things are pounding around, they're hitting the walls more, it's increasing the pressure. And literally, that's sort of the equation you have to know. It's like a simple algebra type thing. P1 V1 equals P2 V2. That basically, if you, and that's what we've done, we've basically cut the volume in half, therefore we have doubled the pressure. It's an inverse relationship. How many people have sort of done that and kind of are familiar with that algebra and are for concentrations? If not, we'll practice that. But for the math problem, okay, we're going to actually use it to breathe in a minute. But for the math problem, what we're going to have is I'll give you 3 of those, and you figure out the 4th. So it's going to be kind of basic algebra. And on those, the lab sheet that we have that I wanted you to print out for pulmonary, you'll see one of those, and there'll be one of those on the test. I'm not going to make it all crazy or anything like that. I'm standing on my head on Mars and doing it. It's simply 3 of those values, you figure out the 4th. But everyone sort of sees this relationship, okay? If you decrease the volume, you increase the pressure. If you decrease the volume, if you increase the volume, you're decreasing it. There's an opposite relationship.
Increase volume, decrease pressure.
Right. In fact, let me just write that. Just kind of in that way. Okay? If you increase volume, you decrease pressure. Similarly, if you decrease volume, what do? You increase pressure. We're going to come to here now. We're going to use that law to show you literally how we breathe in and out. So really we're going to be using that because what we have here, and this is where the idea of these sort of air, pressures in these different segments are, the lungs are contained in an air-filled cavity, the thoracic cavity, in which you have the diaphragm on the bottom here. I can never spell diaphragm, that's why I put it. I'd flunk anatomy because spelling counts. I'd be like, if I taught anatomy, spelling doesn't count, but I'd get in trouble. So, okay, so anyway, there's a diaphragm. This is air filled, and so the key is if we mess with the volumes here, we're going to mess with the pressures. If you mess with thoracic pressure, you're going to mess with lung pressure, and that's going to be breathing in and out. We're going to be demonstrating Boyle's law.
When you keep mentioning lung pressure, you're talking about alveolar pressure?
Yeah. So, I'll put lung here, but really we're looking at the pressure within all the alveoli. That's what's creating it. So, you're ready to breathe in. The steps of breathing in. You never knew there were going to be steps. First thing, look at the diaphragm here. We're going to have the diaphragm contract. We're going to control this. There's some voluntary, some involuntary control from the nervous system, but we are going to have the diaphragm contract. Now look what's going to happen. This is the relaxed diaphragm here. When it contracts, and this can be kind of confusing, is it's literally going to descend. Okay? And that's going to, if you look at this, and we're saying contracting, we were here, and now we're here, which is what happens during contraction, what have we done to the volume of the thoracic cavity? We've increased it, right? We had this much, again, not a perfect picture of that, but from this was better. Right, when it was up here, we had this much airspace, thoracic cavity. Now, we've had that much. So by the diaphragm contracting, we've increased the volume surrounding the lungs, the volume of the thoracic cavity. Does that make sense? Okay, and we can see that. Now comes Boyle's law. If we've increased this volume, which we just have, what's going to happen to the thoracic pressure? Does everybody see? Boyle's law says if you increase the volume, you decrease the pressure. Does everybody see that? Okay, and it makes sense too, right? I mean, now we have this huge space that we had this air in. It's decreasing the thoracic pressure. So I'm putting an arrow down again. That's going to, you can see the relationship, just like we had up there. Increase volume, decrease thoracic pressure. And that's the pressure surrounding the alveolar cells. And so if you're decreasing the thoracic pressure, what are you doing to the alveolar pressure? Okay? If you, this was, the amount of pressure here in the thoracic cavity was pushing on the lungs, we've decreased that. What have we done to the pressure here, therefore? Haven't we decreased it as well? That's pressure on the lungs, okay? They're literally directly related. If we're decreasing the force on the lungs, that means alveolar pressure is lower too. So we've increased the volume of the cavity, that decreased the thoracic pressure. That decreases the alveolar or lung pressure. And if this becomes less than, which it will, atmospheric, what's going to happen? If we've just expanded this, lowered this pressure now is lower than the atmospheric, then what's going to happen? Breathe in. Inspiration. Like, there's a lot of steps just to breathe in, but it works. And again, this one's demonstrating sort of, or using Boyle's law, this opposite relationship. Because it is, that's how we breathe, so I guess we do care about the laws of sort of physics and airflow. So we're breathing in, the diaphragm's contracting, that's, again, just following that, that's increasing this volume. So thoracic pressure is lower, alveolar pressure is lower. When this is lower than this, inspiration. Again, of course, I have those words up there. During sort of rest, like you guys are doing right now, most of the expansion of the lungs is due to the diaphragm contraction. Okay, 60 to 75%. The rest of it are due to, again, these other muscles, which we don't even have to, sort of memorize the name of them at all. But the idea of using the intercostals and scalate is that we've expanded down. You want to expand this way and that way. I'm not going to make you draw like a well or a pump, but that's the idea. To maximize sort of inspiration, that we have to increase the volume as much as we can. So not just downward, but basically both other directions. And that's what these other muscles are going to do. They contribute to the rest of it. If you're exercising, these even have more of a role, because then you've got to expand even more than when you're simply sort of breathing in and out. So simple breathing, most of it is due to, again, the diaphragm, the rest of it through these other muscles, that are expanded. Expiration, the exact opposite, right? The diaphragm comes back, we've lowered the volume, increased the pressure, and we breathe out. I don't need to write that. Okay, it's not the kidney, but hey, we gotta do it. Any questions about that? So you're gonna have to do math with the gas laws, and we'll practice that, but really this is sort of understanding, this pressure differences. Oh, this will be something to write down, though. Because we're going to expand on this, because now, when we're talking about changing in pressure, we've been ignoring something. We've been ignoring the resistance that the bronchiole controls, just like the arterioles control. We have bronchial constriction, bronchodilation, and we want to know how that's controlled. Okay? Let's look at it up here. In fact, so I'm going to make a couple columns here, because I got some additional things to say about it. Because you guys are smart. Bronchodilation, bronchial constriction. What kind of muscles do you think are being used here? Smooth muscles. Okay? Smooth muscles are being used, and just like smooth muscles were used for the veins and arteries, controlled by the autonomic nervous system and hormones, we've got that going here. But let's look at bronchial constriction first. So we've got parasympathetic. Okay, we're used to that. So the idea was, of course, when we're looking at parasympathetic, is that going to be sort of the rest or sort of the active thing, when it's being stimulated? Parasympathetic, what does it stimulate things? Rest, right? It's the opposite of sort of that sympathetic and adrenaline idea. So if we're at rest, do we need as much airflow? So bronchial constriction. So bronchial constriction, we have the parasympathetic. What do you think the neurotransmitter is? Acetylcholine. What do you think the receptors are? Muscarinic. You didn't memorize that for nothing. We're using it right here. Same receptors, same neurotransmitters. Okay? Causing, in this case, bronchial constriction. And so we have that. So, we still got those muscarinic agonist, antagonist questions going on here. And those, you'll see the extra questions. That's why you need to know this. That not only is it parasympathetic that's causing it, remember the neurotransmitter and remember the receptor. What else? Histamine. So we skipped so far a lot of the immune system, but if you have an allergy, an allergic reaction, the idea is something out there you think is really bad that isn't. And so if that's the case, what do you think your body wants to do? Does it want to open your airway a lot more in, or does it want to constrict and try to prevent? That's why histamine binds to its own receptors, and if you have an immune reaction, allergic reaction, histamine is released, and histamine causes bronchial constriction as well. And it just has histamine receptors, so it doesn't have any other name. Okay, that's constriction. Now, dilation. Sympathetic does not innervate the bronchioles, because it's been busy, right? Sympathetic was the star. I had 4 of your columns on the last test, so it's busy. So, no sympathetic. But, who's going to come in? Epi. So, epinephrine will cause bronchial dilation. That's a hormone, of course. Anybody want to guess what the receptor is? Beta 2, right? When it was binding to beta 2 to direct blood flow, it caused dilation. It's saying, okay, yeah, we need more air in as well. It's the same idea. Epinephrine binds to beta 2, bronchodilation. So everybody in half of their nightmares are like, yeah, what is a beta 2 agonist do? The same. If I give a beta 2 agonist, it's going to cause bronchodilation. If I give an antagonist, bronchial constriction. Okay? Right? Because some people still sort of mix those up on the test. Write those down. Always remember that. Okay? If you apply acetylcholine agonist to the heart, okay, to beta 1 cells, what's going to happen to heart rate? It's going to, well, okay, what does acetylcholine do when it binds to the beta 1? It lowers, yeah, so it lowers heart rate, lowers strength. So an agonist will do the same thing. Because some people put all the above. I think I added sympathetic and I added epi and I used an acetylcholine agonist and people put all the above. Some people did. No, it's not. Okay, it does the same thing. If I did an acetylcholine antagonist, that would increase heart rate, like atrophy. But it's the same thing here. So you can look at those questions coming up later too. So you got to also know, because I don't have it here, class notes, that when you're thinking epinephrine, you're remembering that it's binding to beta 2 receptors, causing dilation and increasing airflow.
Beta 2 agonist.
Well, epinephrine binds to beta 2, but if I give a beta 2 agonist, it's going to basically do the same thing.
You said it was going to do what? I thought if you going to create more pressure inside or less.
Which one are we talking about now?
Sorry, the last one you just said, the bronchodilation, that means that those are going to get bigger.
That's going to allow more airflow.
More airflow.
More airflow. So the idea is this is controlling which way it's going to go and sort of how much, but the flow of it's going to be controlled by the constriction and dilation. And again, really, when you look at it, you can see, really, to answer your question more, to look at it more specifically, you can see they're both contributing. The greater the difference in pressure, that contributes to it, but also the resistance will contribute to it too. You don't need to know that equation, though, but I mean, it just gives that idea.
So that would be the resistance.
Yes. So the resistance, just like we had, and I had it up here, the resistance was, that in the arterioles, or in the circulatory system, was caused by how narrow or how wide the arterioles were in veins. It's the same way. This is controlling airflow. Okay? And these are the main controllers of it. Again, the autonomic nervous system and the hormonal system, because smooth muscle. Now, this next section is the lab. And so I don't even want to waste your time in class, because we're going to basically, in fact, let me just kind of show a picture here. We're going to basically, on that machine, measure these different lung volumes and figure out how fast we can blow air out. And I'm going to relate that to obstructive and restrictive lung disease. And how many people did print out the lab, who's tonight's lab? You can see that's where we're going to go over there, and then the other people go over Monday, because it's a little, it's all a little boring, but it's better just to go ahead and do it in lab. So, let me do the cool thing. So, all the stuff covering here, I guess I'll do this one math right here, and then I'm going to do the cool thing, the best thing of the chapter, and then we're done for the chapter for today. Okay, it won't kind of take the whole time. So, we're going to do all those volumes, but this problem, these are problems that we have to do as well on the test. And I don't like this figure, but I want us to just think, and I'm going to use it over here. We're done with this. When you're inhaling, and let's say, I guess I have to just show you one figure here. Let's say you're normally just inhaling air normally, okay? We call that the tidal line. Let me just look, we'll do more of this in lab when you do it. Let's just show you the idea, though, that you're breathing in normal air, that's called your tidal line. You can kind of see about half a liter. Okay, when I did that, did I breathe in all the air I could? No. Okay, you can see that's going to be called, and we'll talk about in lab here, inspiratory reserve volume. How much more air you could breathe in. Okay, when I breathed out normally, did I breathe out all the air? No. That's the expiratory reserve volume. When I did that, did I get all the air out of my lungs? No, remember we said our lungs don't collapse, that's the residual volume. So we're going to play with those volumes, and let's just look at this, because we're going to care about this in lab, so you get an intro to it at least. If we have you inhale as much as you can, and then blow it all out, That's called the vital capacity. You literally, capacities are adding things together. I only cared about a couple of them, but the vital capacity is what we're going to measure. Is basically how much air you can move in and out, of your pulmonary system at any given time. And that's all three of those volumes. Again, we can't mess with the residual volume. It's just what's there. But that's all those, and that's what we're going to test: is your ability to do that and how fast you can do that. Okay, and we're going to do that. But right now, the idea: simple breathing tidal volume. And when I breathed in 500 mils, did all of that reach the alveolar surface for gas exchange? All 500? No, because it's in our upper respiratory tract. And that's called, without looking at this figure, because I hate this figure, I just got to put it there, that's called dead space. Okay? Because, it gets into our body, but it's not reaching the alveolar surface. It's not involved in gas exchange. And we sort of care how much is involved in gas exchange. How much oxygen is getting in, CO2 out. We care about that value. And so when we're looking for that, we are looking for alveolar ventilation. Ventilation is going to be basically how much air we're moving in and out. And so we're going to do, and I'm going to sort of put it up here and kind of use that. We're looking at total pulmonary ventilation. That's just how much air is moving in and out of our pulmonary system, including dead space. But at the same time, we care about how much actually reaches the lung, our alveolar pressure. And so this is how to do it. And this will be, again, a problem that's on your lab sheet that we'll do on the test. We'll have this. We've kind of mentioned it. We'll have our total pulmonary ventilation. Which is going to be sort of your tidal volume, how much you're breathing in, times, how many breaths per minute, those first two columns, okay? I mean, BPM and breaths per minute. And so, and again, tidal volume is mils per breath. So you'll get pulmonary ventilation in something like mils per minute. How much air you're moving in and out. That's total pulmonary ventilation. If you just look at the example, just look at the top line of the example here. They had someone with 500 mils of tidal volume, 12 breaths per minute, 500 times 12, 6,000 mils per minute, or 6 liters per minute. That was their total pulmonary ventilation. So it's tidal volume times breaths per minute. But all that didn't reach the surface. We care about alveolar pressure. So let's use the same numbers to calculate alveolar ventilation, alveolar. You will do, in parentheses, tidal volume minus what? Dead space. And I'm always going to give dead space being 150 times breaths per minute. It's the same, except every breath you're taking in, you have that dead space. Okay, that's not reaching it. In this case, if you look at the top one, that means it's 500 minus 150, which is 350 times 12, because that's the number we give, and that's going to be 4,200 mils per minute, which is what they have up here. Okay, they don't quite show it how to calculate it as easy. They kind of have that, and that's fine. But I sort of just show it this way. Those I'm going to give you values, and you'll see on the lab sheet. It's going to be basically I'll give you breaths per minute and tidal volume, and you need to calculate the total pulmonary ventilation and the alveolar ventilation by simply using those formula. Okay, either tidal volume times breaths per minute, or I'll give you dead space as 150. You subtract that from the tidal volume, multiply by breaths per minute. This was just the example when I had 500. What this demonstrates, and then we're going to do, I'm going to erase the board after that, take a breath, a couple breaths, and do the last thing, which actually is sort of important. I mean, everything's important, but it's sort of actually a little more interesting. But let's show what this sort of illustrates here. What they're illustrating here, they're going to do a couple examples. Like, is it better to breathe fast and shallow or slow and deep? We kind of have an idea of that, but we're going to use math for it. And so what they did is gave a couple examples of how to keep the same total pulmonary ventilation. In this case, shallow but rapid. In this case, slower but deep. And they did it in a way, just for demonstration purposes, so that when you multiply these out, they all add up that the total pulmonary ventilation is 6,000. But you go to this side now, using sort of that bottom equation. If you use that, you actually see that if you're breathing rapidly and shallow, most of that, half of that is dead space. So you're very inefficient. You're not getting much air to the surface for gas exchange. Versus slower and deeper, okay, 600 of that is actually reaching the surface. You've actually increased your ventilation. And anybody that's involved in any kind of athletics know that it's better to have sort of a steady, deeper breathing, not too deep maybe, but you're going to get much better exchange and do much better than if you're sort of rapidly hyperventilating like that. That's not a good day. You're actually decreasing the ability to get oxygen in and CO2 out by doing that. So deeper, slower, better.
Well, people say in athletics, breathe in through your nose and out through your mouth. That really doesn't have anything to do with the amount of air going in or out.
No.
It's something to think about.
That's a good question too. I mean, usually I think it has to do with control, but I hear that a lot too. You're in sort of more control, but I don't know the other reasons because I hear that too. Any questions about that? Simple math problem. Are you ready for something kind of cool? Because I take vitamin water. Okay, this stuff's a little dry. Okay, I can only do so much with it, but it's away. But this last thing I'm going to is cool. Again, everything else we're going to do in lab. Okay, we're not going to have to know that. That's some of the averages for your information. But we're not memorizing that, and we don't care about that. Here, this is important, and I'm going to try to illustrate why what we're seeing here. First of all, what we're seeing, but we don't like tables. So when I first saw this. When I went to Stu's lab, and again, anybody that knows people in Stu's lab, anybody know people in Stu Matz's physiology class? And they're like, his tests are a lot easier. But, hey, that's the way it is. He's a great teacher. He's a great teacher. So he's the one where I basically shadowed his class. I went every day, and he's just such a good teacher. I just know what to say. And really, when it comes down to it, if you're talking to your friends getting in, and you're like, I don't know about Berg, his tests are really hard. If you can get it, I don't recommend every physiology teacher, but I highly recommend him. You'll love his class, you'll learn a lot, and he's just great. But before I went to class, I would always read the book, and I saw this. And I like, okay, what's going on here? Now, we're looking at gases and how they affect sort of the arteries and bronchioles as far as constricting and dilating. And we sort of just did this one, okay, and I'm going to actually put it over here, because you just had a test. If we look at the far right column, the systemic arterioles, we have this idea, I lost my chalk a little bit, if we have, kind of drew this. We had our systemic arterioles, and you can see we're talking gases. I need my little piece of white chalk. I can't use this nub. Here it is. What did we say? If this tissue, and we'll give this example again, if it has low O2, okay, which means high CO2, it's an active tissue, right? And we said, okay, when this happens, we're going to have a local control, and what was this arteriole going to do? It was going to vasodilate, because its job is to deliver O2 to the tissues as needed. Okay, I'm going to make it like jobs to make this make sense. That makes sense, right? Systemic arteries, vasodilate, and we call this active hyperemia. It's only been a couple of days. Okay? If you look over this first column, this is going to make sense. If you look at the bronchioles now, okay, there's my alveolar cell. It's a little crooked. Okay, this is controlling airflow in. If we have alveoli, let's say with low oxygen, what do you think the bronchioles are going to do? Dilate. Their job is to deliver oxygen. So we have the bronchioles under low oxygen are going to bronchiodilate because again, their job is delivery. deliver O2 to the alveoli when needed. That's their job, delivery. Same thing here. The systemic arterioles, their job is delivery of O2 to the tissues. That's how they get paid. Look in the middle here. This is what confused me. Because again, we can use that one where we have, again, they always, CO2 is always opposite. Look at the bottom sort of line here. We have decreased PO2. It's exactly what we said. Okay, oxygen. Less partial pressure of oxygen, we're going to bronchodilate to deliver more oxygen. We look systemic arterioles. If we don't have enough oxygen, we're going to dilate to deliver more oxygen. Look in the middle here. Exactly the opposite. These are the pulmonary arterioles. These are the arterioles. These are the arterioles going through the lungs trying to pick up oxygen. And they have the exact opposite. Okay? The exact opposite effect of both of these. If the pulmonary arterioles are going around an alveoli with low oxygen, they're going to constrict. It's the exact opposite. And I'm like, what's going on? Okay? And I can memorize it. You can memorize this chart, but let's make sense of it. And I made sense of it the following way. At least we're going to make sense officially, sort of by words. But think about it this way. We'll put this up here. Okay? I have, where are my diagrams? I have this one and this one. Let me draw kind of what's up there. Okay? We're going to have two different alveoli out of the, millions that we have. And let's say, again, because we keep talking this one about low O2. This has low O2 and this has high O2. And then we have, as kind of shown there, here are the arterioles that are quickly kind of going through all, going around all those alveoli. So these are the pulmonary arterioles. Now, their job description, exactly the opposite of these. Their job is, we only got a couple seconds here, or less. We've got to pick up as much oxygen as we can to the lungs to get into the body. Okay? That's what we have to do. We don't get paid by delivery, we get paid by pickup. Okay? And if you get paid by pickup, and you've got a choice, which one are you going to go to? Are you going to go to this one or this one? How many say this one? Right? Because again, your job is pickup. If we're right, then we're going to do what over here? We're going to constrict, and what are we going to do over here? Okay, so again, here they actually gave it. This had low O2, this had high O2. If its job is pickup, and we're right, we should see that. So that's why it's the exact opposite. The idea is that it's a completely different system. Pulmonary arterioles, they get paid, again, if you just want to use the job description, again, I use this from my own mind, they get paid for pickup. Their job is to pick up as much O2 as possible. In the lungs, the alveoli. So if they have low O2, they're going to, again, vasoconstrict. The arterioles going to those alveoli and vasodilate, going to where there's more oxygen so that they can maximize pickup. Okay? This had low oxygen. We're like, okay, we're not wasting our time. We've got to get through the system and pick up as much as we can. We constrict there. We actually then will actually dilate to where there is more oxygen, which makes it, if you go to this, why these work exactly opposite as both of these. These jobs, delivery, okay? The systemic arterioles, deliver O2. That's how they get paid, when you need it. So, low O2, dilate, delivering. The bronchioles, same idea. Their job is to provide oxygen to alveolar cells that don't have enough. So if we have low O2, bronchodilate, delivery. Pickup, okay? The idea of pulmonary arterioles, they get paid for how much they pick up. So in these cases with low O2, they're going to constrict so that they can actually pick up as much oxygen as possible.
Does that thing go to the heart?
Say it again?
Does that thing go to after that? After it picks up, then it goes to the heart, right? To
Yeah.
circulate.
Exactly. They'll deliver that through by the pulmonary veins, to the left ventricle, and boom, we can pump it out. Their job is to make sure it's as red as possible, so to speak, as much oxygen as possible. This is quick. Okay, we don't have time to go everywhere. We can go as we want to go to where this is. And the idea of this too, because some people are like, well, why do we have ones that are low and high? When you're sitting there, we're not using all our alveoli. We're only using part of our lung because, again, that's our backup. If we got to run away from that bear, we need to then expand how much air, how many bronchioles we're going to use and how many alveoli we're going to use. So we do have parts of our lung that really don't have as much oxygen. We're not going to waste our time, our blood running through there. We're going to go to where the oxygen is. Now, does everyone sort of get it? Because I think this was just hard. I was memorizing, but it makes sense to me. The other, if you want to be more official to impress your friends, okay, we can look at the word up there and see if that makes sense to us. Or if you don't like the way I do with job descriptions, the way it's basically said is ventilation matches perfusion. Ventilation is how much oxygen we get in. Okay, that's into the lungs. Perfusion is how much oxygen goes to the blood. So, ventilation, perfusion. If we put more oxygen into this alveoli, that's ventilation, it's going to match that more is going to get into the blood, which is perfusion. So they match. So again, I want us to kind of know both. But and it's not going to be, I'm not going to ask you job descriptions, but again, I'll be honest. This is not like this will be a cute way to teach students. This is how I made sense to me. Whenever I'm teaching, it's simply how I remember things. And so I like the idea of the job descriptions overall. But this is good too. And maybe you just want that. That ventilation, whichever ones get more air, more oxygen, more ventilation, it's going to match. Those are the ones which we're going to, it's going to match how much gets into the blood. Okay? Low ventilation, not much gets in the blood. Low ventilation, low perfusion. High ventilation, high perfusion. It's going to match.
So just to, reiterate, pulmonary arterioles dilate when you have high O2?
Yes.
Okay.
Exactly. And, remember the gases. Remember there's always going to be a relationship. High O2 also means low CO2 because you got 4 columns there. So you're always, just like we did before with sympathetic para, you always put those gases in opposition. Okay? High O2, low CO2, and whatever the arrows are. That's why you also will see your low CO2 dilate. They're going to go together. Any questions? So that's what I think is conceptually the hardest thing. In this chapter, everything else is just sort of nuts and bolts. But if you get that, then you can always just memorize this overall if you want to, but I'd actually like you to understand it, sort of that it matches function. It sort of makes sense. So, okay. So that's, again, all the left in this chapter is what we'll actually do in lab. So that means on Monday, we'll actually do chapter 18, or at least do a lot of it. No forget your recorders.